replacement, live drive replacement right there in the 700. So the 700 was basically a very high-tech hardware platform, everything hot swappable, completely custom system that was developed by SpectraLogic long before Will or I came to SpectraLogic. But it was pretty much a hardware company's vision of how to create a storage appliance, right? Take somebody's hardware RAID card, take an Intel server, put it in a nice package with hot swap capability and tiered SAS expanders and plenty of SAS lanes, and then allow the customer to basically run whatever software they want with two options pre-installed by Spectra available, one being Windows 2K3 server, the other being a Linux distribution with Falcon Store. At the time that this product was developed, the concept was we had customers using Spectra's tape libraries. Spectra is well known as a tape library company, and they needed some disk to basically front that tape storage, running their backup software or in the case of Falcon Store, VTL. But there were some problems with this particular implementation. So we had silent data corruption on the Adaptec RAID controllers. This is something that took years to resolve, and quite a bit of expense, having to pull units from customers, things like that. And although we had the ability to recreate the problem in our lab and then show that same problem to Adaptec, we really had no control over being able to resolve the issue. The 700 itself had very high manufacturing costs. SpectraLogic is a low volume manufacturer. Most of our libraries are really big, high ticket items. All the manufacturing actually happens inside Boulder, Colorado at our main headquarters. So kind of expensive in terms of touch time and labor costs to create that thing. When we had other issues with the system with software that was installed, basically it was again outside of our control. So Windows or Linux or Falcon Store, usually more Falcon Store than Linux. And so what we needed to do was figure out, how to address these kinds of problems. And these problems should sound familiar, because when you look at the genesis of the ZFS project at Sun, a lot of the same kinds of issues were coming up. How can we go to less expensive hardware? How can we remove hardware, custom hardware from the equation? So SpectraLogic decided to develop a system to control its own destiny, right? To take these external vendors out of the equation and make sure that we could deliver high quality products to our customers. And at the same time, the company kind of had this realization that although it is a hardware company, the majority of staff at Spectra is developing software. And so we basically sell hardware as a vehicle for our software. So how did we come to ZFS? Well, ZFS provides most of the functionality that via software in a package that allows us to actually see how it works, make rapid changes to it to address customer issues, performance issues, or if there's a change in our product direction. And essentially, because of its infrastructure and basically controlling the entire stack all the way down from the low-level disks through the RAID transforms and volumes and file systems, we basically get to cut out the cost, the complexity, and the liabilities of having a hardware RAID vendor built into the box. Since we weren't quite sure exactly how we were going to package this up to our end customers, it was important to have something that had quite a bit of different functionality. Was it going to be a NAS appliance? Was it going to be a block appliance? Would we do anything with object storage and things like that? It really wasn't clear at the outset. And the fact that the ZFS implementation had already been in production for some time at the time that we were looking at this was a key plus. I mean, coming from a well-known and respected engineering organization at Sun, already integrated into the operating system that we ended up using, all of those things were important characteristics of ZFS in choosing. So what about ZFS on FreeBSD? Well, actually, before I joined Spectra, it was ZFS on OpenSolaris. And so all the prototype work of this initial product was done using OpenSolaris. But then Sun and ZFS had what I like to call its USL moment. And for those of you that aren't aware of this, back in the early 90s, FreeBSD and all the BSDs, NetBSD, this was before OpenBSD and DragonflyBSD, really had a big hit in their uptake because of a lawsuit with USL about basically claiming that the University of California had infringed on copyrights for AT&T use. And that particular hiccup in BSD's uptake, we still are feeling it today. I mean, if you look at the uptake in terms of user base and things like that, it basically was going up, it flattened, it went down, and then it kind of carried on its original trajectory. And so in this case, SpectraLogic decided that there was too much uncertainty, right? They had just come from developing a product that they could not control. And so anything that came into that picture that gave them the feeling that they wouldn't be able to control the future destiny of the product instilled a considerable amount of fear and a pretty swift reaction. Now, the prototype was already pretty far along, and so they decided they still wanted Zfs. And in order to be able to do that, really at the time, this was in the middle of 2009, the only alternative was FreeBSD. And that's where I came into the picture, sort of after that decision was made. Same thing with Will. We actually have 3 committers on staff now, people that can commit to the FreeBSD source tree, Ken, Mary, Will, and myself. So what do we want to do with this technology? Right? Spectra's strength is tape. People love our tape. They love our support of tape. They love the fact that we're creating technologies that ease the pain of using tape. So the idea behind this product is to use ZFS's data integrity features to be able to span wherever your data happens to be, right? So you create a data set. Potentially that data is like in a media and entertainment environment. It might be on somebody else's system. It might be on a plate air server or some other kind of asset management system. Basically taking that the ZFS checksum capability and exporting it to partners means that we can ingest data with the checksum data already embedded in what we're transferring. And then we can turn around and make sure that those checksums not only reside in data sets on disk, but also go to tape. So you have this additional data guarantee as far as that you've saved your data properly, that you are able to restore it correctly, taking that whole data integrity story, and that's what we call archive-grade storage. The other thing that we're trying to do is to, again, ease the burden of using tape. Tape should just be kind of transparent for you. And so allowing customers to create workloads and basically a profile of what their data reliability and restore capabilities are. They can basically do that once within the system and then allow our appliance to manage that. So whether you need near-term restoration capability that we do with snapshots, if you need something for disaster recovery, that might be in tape, or it might be a mixture of both, right? Depending on how we migrate the data for you. So I started in 2009, Will started in 2010, same thing with Ken, right? Several other people have joined the group since then. Why has it taken so long? Well, there was this implicit assumption within Spectra that, hey, ZFS, rock solid, man. We were prototyping this stuff on OpenSolaris. I mean, it's awesome, right? And then we prototyped it on FreeBSD, still worked really great. But in order to provide a real end user experience with that technology, it takes a lot of work. And it's not just being able to glue together pieces that you read the man page for. And so a lot of what's gone on inside Spectra as we work towards releasing a product, hopefully sometime at the end of this year, is negotiating with management about, well, how things really work, and the difficulty of doing integrations, and also determining what the best way to present this technology is to our end customers. So the first go at this system was actually way more complex than what we're trying to deliver today. The prototype with OpenSolaris, and then again with FreeBSD, involved Zen and Windows and Linux VMs and basically the entire joint product, I would think, in a small appliance, but developed with a very small team. And it was just more than we could achieve. I don't want to bore you with issues with trying to integrate with Zen, but it was very, very painful. Spent a lot of time doing that. We had some issues with ZFS, which I'll talk about in another slide here. But it was just too much for the team. And it wasn't really targeted towards meeting a particular customer need. We needed to really focus on what it is that Spectra does for our customer and deliver just on those things, instead of just saying, well, we'll throw virtualization in there and let them install whatever VM they want, which will take care of, data management and things like that. So some ZFS specific issues that we ran into. This has been mentioned earlier in the day, but probably the biggest one was synchronous copy on write fault resolution. And so just to describe this once again for those that aren't quite familiar with it, ZFS writes things in record-sized chunks, let's say 128K. If you happen to start even a streaming write transaction in the middle of a block, ZFS will dutifully perform a copy on write fault on every single block, and it happens synchronously. So you start in the middle of a block, 120K, let's say you started 64K in, it says, I don't have the first 64K, how can I write your data to a new data block? So it blocks you, it reads the 128K old record off the disk, merges your data in, and then writes it to a new location. ZFS is also, as it stands right now, unable to be patient enough to wait for additional data to come from the user. So in an ideal world, what would happen if you did a a streaming write transaction that was unaligned, is you'd have a copy on write fault at the beginning and a copy on write fault at the end, wherever you had two runt blocks. But everything in the middle, you're completely overwriting anyway, and there's no reason to reclaim or to read that data off disk. There's no metadata information that ZFS needs to be able to free those blocks or any other information. So what we did at Spectra was we first encountered this primarily in the use case of running virtual machines on top of ZFS, where you have another file system that doesn't really understand the record nature of ZFS, and you're getting copy on write faults all the time. In fact, the worst case for us, we had kind of two competing goals here. We had a Windows VM with carefully constructed file system trying to align NTFS's cluster size with ZFS's record size, and also trying to have fairly large ZFS records because we were using RAID Z. We're an archive kind of product. We wanted to basically provide as much storage as possible to the user, so we were doing RAID Z. And you need a fairly large record size in order for RAID Z to perform well on streaming operations. But we'd see this huge performance penalty as we grew the size of the ZFS record, because unless you made it fairly small, you would constantly get these extra reads. Okay? So Will and I basically partnered for, I don't know, 3 months or something like that. And this was our first deep dive into ZFS. Until we basically took on that project, we were just consumers of ZFS, right? We understood how to create snapshots and how to hook that into our management layer and creating file systems and things like that. But this was a case of having to really go down into the data management unit layer of ZFS and completely understand what's going on. And this is one of those experiences where you know that all the people that wrote the ZFS stuff, they're truly brilliant, right? And you've probably, if you've ever been a software developer, you know when you're in the zone, right? You don't usually write a lot of comments, right? I mean, it's just obvious, right? And so as an outsider coming into ZFS, you're sitting there and you're like, I think this is a bug, but is it really a bug? I mean, maybe he's just too smart for me, So that was kind of the experience for 3 months as we did some pretty challenging and pretty intrusive changes to the data management unit, so that essentially if you're not a synchronous writer, we basically grab your data, we track where it belongs inside of a record, and we will, in the background, do the fetches. And in the case of a stream that crosses multiple blocks and fills in those blocks, we don't do the reads at all. Anyway, hopefully the first of many improvements to ZFS that we'll be pushing back to the community. The other issue that we ran into is because again, at the time that we were doing a lot of these optimizations, we were trying to be everything to everyone. We also wanted to be able to pass ZVol data, so ZFS volumes, out through either iSCSI or Fiber Channel or some other kind of block interface. And these block consumers really want to operate in an asynchronous fashion. But the data management unit layer really wants to behave, at least as far as reads are concerned, in a synchronous fashion. And so what Will did primarily was to rearrange that API so that it could serve both synchronous and asynchronous consumers, so that we could basically figure out, encapsulate what the request was from somebody like an iSCSI or a Fiber Channel target, and retain that information, run it completely through the DMU, and then offer callbacks to those consumers. The other thing that we ran into in FreeBSD is that in Solaris you have the Solaris fault management framework and all these things, and ZFS is really tightly coupled with them in terms of how you report errors. A disk has gone away, a disk has been returned, all that kind of stuff. So we had to basically write a very watered down version of that, which we call ZFSD. That's actually already in a project branch in FreeBSD, but we had some additional enhancements to that. I'm hoping that that's a temporary contribution to FreeBSD. One thing that the FreeBSD Foundation has been trying to find somebody to work on is a comprehensive fault management framework for FreeBSD. It's a crucial need. In this case, we did enough for our product, and it's probably enough for many consumers of FreeBSD, but there's certainly more work that's needed there. And then lastly, coming up with a UI that is understandable to guys in IT who aren't necessarily familiar with ZFS. And RAID Z in particular is kind of troublesome in that nature. A lot of folks are familiar with RAID 5 and RAID 6, and you say, oh yeah, well we have a single parity drive, or we have 2 parity drives. So, oh yeah, just like RAID 5 and just like RAID 6. No, not quite like RAID 5 and not quite like RAID 6. Although, as far as the data integrity guarantees, that's the case. And so even within our own management, it was kind of hard to convey that the performance characteristics are different, and that you have to somehow configure the pool or configure the product in order to be able to take that into account and still provide the end customer story that we're looking to achieve. So as I mentioned, the RAID Z issue, that's still an issue for us in our product in terms of what at least our target customer is expecting in terms of performance. We also, again, in terms of being able to make things simpler for end consumers to understand, in the case of a ZIL or an L2 ARC, it'd be hugely convenient to be able to say, how many IOPS of the ZIL would you like to devote to this data set or to this pool, right? So if you have consumers of an appliance and they say, well, I have different data set requirements, like here I want to do a mirror because it's very IOP driven. Here it's cold storage, so I'm going to use really long stripe sizes in my RAID Z. But I would like to have the go faster button, right? I would like to be able to say, yeah, give me some SSD with that. And depending on how many slots you have in a chassis, it's kind of inconvenient to say, well, you need to buy another drive for that. I know it's a really small pool, and that maybe it doesn't get as many IOPS or during the day, or it has just only certain hot times during the day. But unfortunately, it's either that or invest a lot of infrastructure in our product to dynamically partition an existing SSD and all that kind of stuff. And so it'd be really convenient to be able to share those resources across pools. Since we do have an application layer, the stuff about libZFS core, we're very excited about that. We also are looking at integrating other kinds of object storage APIs into our product, like Amazon S3. So it'd be nice to have a public API to the DMU that's exported to userland for use by things like web agents and things like that. Z-test, yes, we found several issues. I'm trying to remember if they were all because of things that we did, which is of course our fault, but one thing that doesn't happen inside Z-test right now, and for those of you who don't know what Z-test is a userland instance of ZFS that runs a whole bunch of really terrible torture tests against ZFS. Hugely beneficial if you're a developer in ZFS to be able to run this stuff on the bench without crashing your system all the time. But one thing that it doesn't exercise is a lot of the IOCTA paths. And if you're an appliance and you have different agents in your system constantly polling the system or looking for events and things like that, you really want to inject those events into the test stream while you're doing all these terrible things. Like, what happens if I try to get status on a ZVol while the pool it's in is getting re-GUIDed or something like that? So we have a little bit of work towards that, but we definitely want to extend that more just so that we feel like we're getting more test coverage where we're using Ztest. We've also done quite a bit of work of getting the STF, the Solaris test framework, with its Zfs tests running on FreeBSD. That's another thing that we're in the process of contributing back to FreeBSD. Spares. Spares was kind of a recent surprise for us. So for a while, the product has supported replace by physical path, right? We have an enclosure device that tells us the physical path of all the drives. We added support to FreeBSD to be able to record that inside of ZFS label information. So you basically pull out a drive and put it back in the same place. Everything magically happens correctly. In the case of spares, though, we were kind of saddened to find that it requires devices to be opened multiple times if you decide to take a spare and assign it to multiple pools. And so our version of ZFS on FreeBSD is probably the first place where we don't open those devices exclusively. In order to be able to make sure that spares work. And so that's an area that I think needs just a little bit more cleanup so that we can track spares more intelligently, provide a global spare where we basically say, I've labeled this drive, it's a global spare, feel free to do what you want with it and not have to assign it to every pool in the system. Or if you want to do private spares and share it across multiple pools in the system, that you don't have to open that VDEV multiple times. Because without the exclusive opens, an administrator actually can go right to a disk that has ZFS on it, and that's not a great thing. And then the last one is a tie into archival use. So in our situation, what we really want to be able to do is take advantage of ZFS send and receive streams to be able to intelligently archive your data and transfer it from whether it's spinning disk or flash onto tape. In that case, though, it's great for disaster recovery. If you want to restore a complete pool, or if you happen to have a snapshot that's fairly recent and there's only a few incremental snapshots that you have to restore in order to be able to get your data, that's great. But what if that was 6 months ago or 2 years ago, and all you really want is a single file? Well, how much storage space does your pool take, right? Do you even have that data set on your disks anymore? So one thing that we're very interested in doing is being able to filter the restoration of data so that we can do incremental and file level based restores. And there are probably lots of other things that I forgot to mention. But from the list, hopefully you can get the sense that we're very excited about ZFS. There's lots of, it's just like any other project, right? There's always something to be done. And here's just our laundry list, things that we're going to be working on. And we hope to collaborate with lots of others. So Spectra remains committed to ZFS. I don't see that changing in our product anytime soon. It's just too cool. And Spectra remains committed to FreeBSD. And our disk products and other products from us that deal with intelligently managing your data and getting it to and from tape will probably continue to use it for the foreseeable future. Yes, I highly recommend it, although a quiet place.
3 months.
And 3 months, yes, absolutely. Any questions? Okay, so the question was about the copy on write fault improvements. How generic is that? And how soon do you think you'll be pushing it out?
Well, the copy on write fault improvement are primarily within the DMU lab, and the DMU lab is a very portable system code that runs on any implementation of ZFS. So we believe that the changes made to the DMU should work on any other port of ZFS. And we have tried to write code that is reasonable as far as how easy it is to understand and how well tested it is.
So as far as the time frame, I mean, there's a hackathon tomorrow, right? So, no, I mean, the main issue that I see in terms of the timeline is, again, they're fairly invasive. So, and there's also a lot of things around the periphery of what we did that probably need to be pulled out and reviewed and committed separately. So part of what Will and I are going to be doing tomorrow is going through that massive bolus of changes and trying to figure out exactly how we can cut it up and get it into a state where it's easily reviewed. So hopefully soon. Here.
Since you wear the FreeBSD T-shirt,
I'm sorry, but this is a Lands and nice dress shirt with an embroidered logo. Okay, so we don't mess around.
What's the status of high availability of FreeBSD, and do you have any plans of bringing that to your storage?
If you're talking about high availability storage, the HAST daemon, is that what you're talking about, or just?
No, just in general.
Okay, so Spectre does have a lot of interest actually in high availability and bringing it to its product set. It's not clear if that's going to be a generic FreeBSD capability that we contribute back to the community or not. There have been several, speaking with my FreeBSD Foundation hat on, there have been several initiatives that the FreeBSD Foundation has funded. For instance, the HAST daemon, which is kind of like DRDB in Linux. And so we're always interested in seeing proposals for items like that contribute to high availability. In back.
Your need for the global spares.
Yep.
Are you envisioning that's just something that you need on a given local box, or do you just have a global set of disks that are accessible?
So the question was about global spares, and do we envision that being spares that are just available for a local box or across multiple boxes? And
well, that obviously depends on if you can Zfs to what kind of cluster everything, right? Just because I know that's happening.
yeah, so I think that right now we'd be happy if you could just put a label on a drive that says this is a global spare target, use at will, and it's whether it's ZFSD or the fault management framework in Lumos or whatever, then you'd have basically global spares.
A question on the screen here. What type of performance hit do you experience with multiple VMs with copy on write faults as opposed to over just one VM?
So the question was about copy on write faults with multiple VMs. I don't know what you want to. Do you want to take that?
We didn't really have a thing where we were trying to run more than one VM at a time. So,
well, we had multiple VMs on a single pool. Absolutely.
yeah.
Right. So I guess the way I'd answer that is that essentially we saw in some cases, a 10x reduction in read traffic. And so whether you have, basically it's 10x of one VM or two VM or four VMs.
Actually, it's more like 100x.
Yeah, depending on the scenario. So it's good for everybody. The only downside, I guess, would be that there is some additional memory accounting and stuff like that, but the overhead really isn't that much larger than what you'd also see just in the synchronous resolution case.
Okay, we're ready to move on to our next speaker.
This is great stuff, guys. Maybe.
Just mirror display.
Give a hand. I'm not familiar with that. So we'll see some usage. Thank you. Okay, my name's Brian Behlendorf. I'm a developer at Lawrence Livermore National Laboratory. I thought it would be interesting today to talk about actually a different perspective on ZFS. I work on high performance computing, which I don't know that ZFS has a lot of exposure to just yet. In particular, I wanted to talk about Sequoia, the new high performance cluster at Livermore, which now uses ZFS. So I got interested in ZFS a couple of years ago when the plans for Sequoia came across at Livermore and we started looking into it. So Sequoia is it's a very big machine. So right now, Sequoia is the #1 supercomputer in the world. It is, in terms of measuring performance on these supercomputers, people usually use a benchmark called LINPACK. Actually, maybe let me take a step back for a minute here. This is a different crowd than I'm used to talking to. I come from an HPC background. Usually everybody, it's kind of a small community, so everybody knows how it all works, but let me try and fill you in a little bit. Clusters these days are measured with a tool called LINPACK. It's basically just a benchmark that solves a large, dense system of linear equations, and how fast you come to a good solution basically measures the performance of the system. So Sequoia turns in a number of 16 petaflops, which is right now #1 on the top 500 list, which is the top 500 list of computers out there. The nearest competitor is a system called the K computer, turns in a number of about 10 petaflops. Behind that is a system called Mura. It's another DOE lab at about 8 petaflops. And bringing up the rear in the top 10, there are a handful of maybe 1 and 2 petaflop class systems. So there are very few of these systems out there. And the point of these systems isn't to run LINPACK and get numbers for performance metrics, although it's nice to be at the top of the list. Everybody wants to be at the top of the list. The point of these systems is actually to run large simulations. So Sequoia is right now on one of our open networks, and it can run, it's basically getting deployed right now, but it will have a variety of codes run on it. Sequoia is built, this is a high-level architecture for Sequoia. It's constructed out of 1.5 million cores for these simulations. Some people say 1.6, depends how you round. What's 100,000 cores here or there, right? I get dinged a lot for that, actually, those slides was 1.5, but I round down, I'm conservative, what can I say? Those cores are spread over 96,000 compute nodes. So that's the compute engine for Sequoia. That's what does all the processing. But real jobs, unlike LINPACK, actually have to pull data off disk, right? They have to read in their initial conditions. They have to write out checkpoint dumps. They have to read those checkpoints back in when the system fails or there's a problem. So there's actually a need for not just the compute number, which is what gets all the press, but an actual huge file system for Sequoia to store all that data and pull it back. So Sequoia is attached to a parallel file system. So one of the most scalable parallel file systems out there right now is a system called Lustre. It's a distributed parallel file system that runs on Linux, and it's basically allows you to aggregate a huge number of servers into a single mount point. So Sequoia has 768 client nodes, I/O forwarding nodes that mount the Lustre file system. And they each connect to all of the 768 servers for Sequoia and aggregate the bandwidth together. Those I/O nodes in turn act as forwarders onto the compute nodes for all their I/O. Each of those 768 storage nodes has 72 terabytes of data behind it, basically usable storage. So 72 terabytes times 768 servers gives us a 55 petabyte usable file system. So this is one mount point on one I/O node that says if you run df, right, it says 55p after it. So it's a big file system, right? It's pretty cool to see, actually. Try that again. It just timed out. So that's cool. So we've got a huge file system, right? And that's a lot of disk. And we need decent bandwidth to it. So all these nodes are connected through QDR InfiniBand. Each node has a QDR link, and through the switches. And there's about 1.5 terabytes of bandwidth between all the clients to all the servers. For the Lustre number we're targeting, we're hoping to get about 1 terabyte a second of that bandwidth actually delivered to the applications. But here's the problem. Lustre's built today on top of, each of these storage servers is built on the top of the ext4 file system and Linux, which has been a staple. It's been around for a long time. It's stable, it's well tested, but it doesn't scale particularly well, right? We've got, at this point, a lot of disk for Sequoia that needs to be managed, right? So this is one row of disk for Sequoia. It's one of several rows of disk, right? Each rack has 8 60 disk enclosures in it, and they're all populated with, 2 terabyte nearline SAS drives. So there's about, I think it works out to about 24,000 drives in the file system, spread over all these nodes. And we've seen for a while now that ext3 has been coming up, or ext4 now, has been coming up on its limits of scalability and performance. So when Sequoia was proposed 3 years ago now, we weren't sure that ext3 would be able to scale to meet those needs. So it turns out that I think it probably would have worked for Sequoia in practice. It would have been good enough, but you got to keep in mind that Sequoia is one of many steps. It's not the end of the journey here for high performance computing. So we will build bigger machines, right, in the following years. There are plans on the books to build exascale class machines by 2018 or 2019, and they're going to be 1,000 times bigger. So while ext4 probably would have worked for Sequoia, it's not going to get us where we need to be long term. ZFS, on the other hand, is much more scalable and provides hope that we'll actually be able to build these machines. So why ZFS? I'm kind of preaching to the choir here. This is more of a slide for the HPC community and not the ZFS community. But it gets us what we need for HPC, which is massive scalability, right? ext3 at the moment has a limit of about 32 terabytes per file system. You can go bigger, but you may have trouble finding support for that. And data integrity. Data integrity is a big deal for high performance computing. It may not be a big deal for a lot of other workloads, but when you're doing huge simulations, every bit's got to be right? Or the simulation goes off the rails. So data integrity is a big deal. We did not have that with the ext4. We ended up having to buy expensive hardware RAID that checks parity and read, and we had other solutions for it. Lustre happens to protect the data integrity over the network. ZFS protects it on disk at this point. We'd like to unify the two, but that's probably still future work. And cost is frankly an issue. I mean, you saw how much disk was up there. That's not cheap, right? So eliminating as much of the hardware components as we can, moving it all into software with just simple JBODs, that's a good move for us. We have enough disk and enough in-house expertise that we're not too scared of moving to inexpensive disk and JBODs and taking on the management ourselves. We're a big enough site that that's worth doing. So I would say that's actually Livermore's interest in pushing ZFS forward on Linux. I guess perhaps one point I should have made earlier is that Livermore is a Linux HPC shop, which means that pretty much all of our infrastructure is Linux. Our clusters run Linux, our storage servers run Linux. We're Linux top to bottom. So while ZFS was cool technology, when we looked around, we really wanted it on Linux to integrate with Lustre. There were other solutions for Linux, XFS, or when we started ButterFS didn't even exist. But Linux or ZFS was clearly the right thing to do for high performance computing. You don't build a new file system, for example, in just a couple of years and trust it. So why did we port? So it turns out that our main interest for ZFS was getting Lustre to work. And Lustre really wants to tie in directly to the DMU layer in ZFS. I'm sure you've seen a variant of this picture before. So for Livermore's purposes, we only really needed to port the transactional object layer and the pooled storage layer. And then there was a lot of work to get Lustre directly integrated with the DMU. So we did that. We ported, it took us a year or two, but we ported those two layers over, and the Lustre work is just wrapping up now. The code's out there running on Sequoia. And that worked pretty well. In fact, it worked so well that we were encouraged enough to bite off porting the rest of it and get the POSIX layer in place and the Zvols in place. That's much newer work, but I have to say it's actually gone really well. It was a lot more challenging, I would say, than porting the transactional object layer and then lower things in the stack, which is pretty independent code, whereas higher level interfaces are very different on Linux than they are on Solaris or FreeBSD or any of those variants. It's a very different APIs to work with. So a lot of that code had to be rewritten for Linux. We tried to use as much as was possible in the existing stack, but at the end of the day, you have to integrate cleanly with the Linux APIs, or things just won't work right. So that was actually quite a bit of a bigger effort. But it's an effort that really paid for itself in the end. So while we were just working on Lustre and the transactional object layer, right, and everything below it, there wasn't much interest in the Linux port, right? It was kind of a niche thing because who else has a supercomputer that they need this for, right? There wasn't a heck of a lot of interest in that. So while we needed it, it was kind of niche. But once we got the POSIX layer in place and the Zvol is basically functional, a whole new community of ZFS users showed up saying, this is cool, can we help? So one of the nice things about it is suddenly there's a lot of interest in the Linux port and a nice community that's sprung up around it, which has been, frankly, in my opinion, invaluable. Just from willing to grab the code and test it on their system, to filing bug reports, or I get a lot of patches these days from people in the community for little things, right? The code's very easy and accessible to work on now. It's all on GitHub. It's easy to build. So the community has really taken it and run with it, and I think it's been great for the stability because once you get into the hands of the masses, they try every crazy thing you could think of with it, right? And they found very interesting bugs that we had missed, right? But we have a very targeted workload with Lustre, right? We have servers, we know what they're going to do. We made that work well, but there's all kinds of crazy people doing things with ZFS on Linux these days, and I think it's actually really neat. So where are we at today? So we have a stable release candidate on Linux. I mentioned before, I'm a file system developer, so that means I'm inherently pretty conservative. So while I'm calling it a release candidate, it is running on a huge supercomputer at the moment, 24/7 without trouble. It will probably run fine on your NAS box. It will probably run fine in a lot of places for most workloads. But, you know, until that code has been soaked for several months, and major issues have been run down, I'm a little reluctant to call it stable. When I call it stable, it's stable, right? So I'm hopeful that we'll be able to drop the release candidate extension, but at the moment I don't, it's very stable, but I'm still sticking with it. I happen to use it at home for all my stuff. I trust it implicitly, but that's different. So community, I mentioned this just previously. There are now actually packages out there. So Livermore's been maintaining the upstream tree for ZFS. We've had downstream maintainers step up for various Linux distributions. That's actually really helpful for me because Linux, maybe unlike a bunch of other distributions, it's highly fragmented. There are just a ton of Linux distributions, and each one has their own right way of doing things, right? So there's no way we at Livermore can support everybody's right way of doing things on Linux. So every downstream distribution is going to pick up the software and repackage it for their distribution, how they want to work. So right now, probably most people get exposure to it through Ubuntu. There's a PPA. You can just add it as a remote source, do apt-get install ZFS, done. Support has been integrated into Gentoo Linux. It's also shipping in Sabian Linux, just as part of the distribution these days. And we provide generic RPM packages for Red Hat or CentOS or SLES. There's a website, lots more information there, and mailing lists that actually have a really quite a good community discussion going on. So that's all I've got. Questions?
What version is equal, and is it Q's username or parallel?
No, so actually it's version 28 is the last thing that was released officially. It all runs in the kernel. This is not a fuse port. There is a fuse port out there, which I probably should have mentioned. It's still a slightly older Z-Cool version, but this has nothing to do with that. This was built up from scratch. And as for the licensing issues, we distribute everything as source at the moment, but we don't believe that there really are any other licensing issues around that. There's been a lot of FUD in this area, but it's our opinion that that's just fun.
So the number that I quoted, there were 700 commits in the past 2 years. Does that seem right from your experience?
Yeah, it's about ballpark. Yeah, I believe that. I'd have to go look. So we've been busy. And I have to say that actually one of the great things from the community is that more recently, most of those commits have not been coming from Livermore. They've been coming from other sites. In particular, there's been a lot of people who've been backporting things from Illumos. We'll get patches saying, here, they just put this feature in Illumos. It would be great to have over here too. So we'll get patches for that and get them reviewed and in the tree.
I just counted 756.
756. Okay, so I just heard 756 is the latest count.
What's the story with the Luster as something reported in open that would also be available for other Zfs platforms?
You need an equivalent for Luster?
Is Luster itself tied strictly to Linux, or is there interest in having it also be like Zfs available on Illumos, FreeBSD?
So the question is Luster available on other platforms, basically? The Luster folks aren't opposed to that, particularly. In fact, they've made several efforts in the past to port parts of it, the Luster client, the Luster servers, to Solaris and macOS. Unfortunately, Luster is, well, you saw from the architecture, Luster is a big part of the diagram. Zfs is, in fact, a very small bit of our picture for the Luster, right? So right now, Luster is only available on Linux, but it's only because the development for other platforms hasn't been funded by anybody else. And there doesn't seem as much of a need for it on other platforms, because most of the supercomputers and clusters these days where it's really useful seem to run Linux.
Luster would be more useful than that actual security, and sadly it doesn't. So
this is true. There are features that should be in Luster, but
on the roadmap that it disappeared.
Well, yes. There are actually quite a few features in Luster I would like to see too, but.
So if you guys have more questions about Linux or FreeBSD or any of the other platforms after lunch, we're going to have a panel discussion and talk about kind of compare and contrast all the different platforms that Zfs is available on.
Thanks.